Okay, we're going to talk about cycloalkanes in this chapter. And the first thing I want you to realize is if you build models for cyclopropane, cyclobutane, cyclopentane, and then cycloalkane, and use those models as you work along in this chapter, it will really help you to understand this a lot better. Because we're talking about three-dimensional things here. And this PowerPoint, this online lecture, is 2 dimensions. So it's very hard for you to visualize this without the models. There are a few of you out there that can take a picture and make it a model in your head, and that's great. But the majority of you are going to be needing to build a model so as to be able to touch and feel it and understand this better. Cyclic compounds are really important. We have them in nature all over the place. For instance, glucose exists as a cyclic molecule, as does ribose, which most of you have taken biology and understand those are important parts of biology. We also have them in prostaglandins and in steroids. This is a multi-ring compound. Notice that. Here, prostaglandins have a 5-membered ring. There's 6 and 5-membered ring down here, and we call these fused rings. So in order to make a ring, what you have to do is take an open chain and link it back on itself, but to form that bond that connects a ring into a ring, you have to remove 2 hydrogens. So the general formula for any ring that is all single bond, there we go, brought it back. Right here we have cyclopropane. Cyclopropane has 3 carbons in it and 6 hydrogens, and we just draw it as a triangle. Cyclobutane has 4 carbons in it and 8 hydrogens, and we draw it as a square. Cyclopentane, 5 and 10, and we draw it as a pentagon. And then cyclohexane is, of course, a hexagon. Notice these have 3-dimensional structure. Although this is planar, this cyclobutane is puckered slightly. You notice that in this drawing. The cyclopentane is puckered slightly. We actually call this conformation the envelope conformation. And then right here, cyclohexane is puckered twice, and we call the conformation that it's in here the chair conformation. We'll go into that later. So go ahead and you try and determine which of these formulas can be a cycloalkane. The only one that can be a cycloalkane is C5H10. There's too many hydrogens here. This would be an open chain propane, and there's too few hydrogens here to be a cycloalkane. This actually could be a cycloalkene with a double bond in it, because a double bond will take away 2 hydrogens. If we go to name the cycloalkanes, what we do is we count the carbons in the ring and we name them cyclo, and then however many carbons are in the ring gives us our prefix and then ane. So if I look at this is a cycloalkane, but notice there's substituents on it, so we have to name and number them. What we always do is we pick a carbon to be our number 1 carbon. The number 1 carbon can be anywhere in the ring. Notice down here, it's over here on the right, over here on the left. It's not always at the top of the ring. We just happen to have drawn it that way here. Now if I look at this, I am going to number these to get the lowest numbers. So I'm going to say 1, and I could go 2, 3, 4, 5, or I could do 1, 2, 3. If I do it this way, that gives me higher numbers, 1, 5, then 1, 3. So this would be 1,3-dimethylcyclohexane. Likewise, if I go down here, I could number 1, 2, 3, 4, or I could do 1, 2, 3, 4, 5, 6, or I could do 1, 2, 3, 4, 5, 6, 7. All those would give you higher numbers. This gives me the lowest set of numbers for the substituents, so I'm going to call this 2-ethyl, notice 2 carbons, and then 1,4-dimethyl cycloheptane, because there's 7 carbons in there. Notice I put the ethyl first. Why? because E comes before M alphabetically, and we list our substituents alphabetically. The D in the di or tri or tetra is not counted as the alphabetical part of the substituent. However, you're going to see that if the substituent is called something like isopropyl or T-butyl, we do take that and consider it as part of the name, because if you take that away, you change the structure of that substituent. You just don't, in counting the numbers of a particular substituent, you don't use the di, tri, and tetra. Okay, let's look at a ring. When I look at a ring, there can be no rotation about the bond because this carbon is holding those two carbons and preventing them from rotating. This means that there's a side to each ring. There's a top side to this and a bottom side. Right now, the top side and the bottom side are identical, so flipping it over would not make a difference. But just keep in mind that rings cannot rotate around those bonds. If you want to, get a model and try, and you will see. The sides of the ring make it so that you have cis and trans isomers. Notice this methyl and this methyl are on the same side of the ring, the up side. If I look at this, though, one methyl is up and the other methyl is down. As a result, we call this cis 1,2 dimethyl cyclopropane, and we call this one trans 1,2 dimethyl cyclopropane. We've learned about isomers. Isomers are structures of the same compound with different connectivity. Here the connectivity is the same because it's this carbon has a methyl attached and that carbon has a methyl attached. But what's different is this one's up and that one's down. So we call these cis-trans isomers. They're a type of stereoisomer, and so sometimes we'll call them cis-trans stereoisomers. A stereoisomer is a compound that has the same connectivity but does not fit in the same space. So you see that I cannot take this and put it inside that one and reproduce it. So we call these stereoisomers. Okay, what I want you to do right now is go ahead and pause the lecture and figure out which ones are cis and which ones are trans. And then restart the lecture and we'll go through these. Okay, if I go ahead and I look, I can see this is up and this is up. So this one's trans. But this one's up and this one's down. So that one, excuse me, let's start over again. This one's up and this one's up, so that is cis. This one's up and this one's down, so that is trans. If I look, you can see this hydrogen's up, so the ethyl is down. If I look at this one, this methyl's up, so the hydrogen's down, so this is trans. This ring has a methyl up and an ethyl down, so it's trans. This ring has one substituent up and one down, so this is trans. These are the cis here, and these are the trans. All right, stereoisomers, I already talked to you about this. Constitutional isomers have different connectivity. If I look at this and this are constitutional isomers. Why? Because the way the carbons are connected is different from the way the carbons are connected here. However, if I look at this is a stereoisomer because there's a carbon attached here and there's a carbon attached here, and over here there's a carbon here and a carbon here. They're identical except for one little thing. These two are cis on the same side and these are trans on opposite sides. And there's no way I can take this and put it inside of this. So we say they are non-superimposable, or you can say they don't fit in the same space. As a result, we call these stereoisomers, and the particular type of stereoisomer is cis-trans stereoisomer. So look at these and tell me, are these conformational isomers or cis-trans stereoisomers, or are they the same molecule? Pause it, and then we'll go over the answer. Okay, so if I look at these two, you can see that this is 1, 2, and this is 1, 3. Although they're both trans, 1, 2, and 1, 3 are different connectivity. So these are conformational isomers. Okay, again, pause the lecture and determine which type are these, conformational isomers, the same, or stereoisomers. If I look at this one is 1, 2, 3 trimethyl cyclobutane. And notice the methyls are up, down, up. If I look at this one, you can see it's trimethyl, 1, 2, 3 trimethyl cyclobutane, but now we have one up and one down, but the other down is the same as this one. See, this is alternating, and this is 1 and then 2 down, not alternating. So if I go back these to are this, stereoisomers. These structures here, I told you they were puckered. When the cyclopentane puckers, it actually causes a reduction in this bond angle and increases the ring strain. When the cyclohexane puckers, it causes the bond angle to become 109.5 and a perfect tetrahedral shape. So the cyclohexane ends up having no ring strain, and cyclopentane ends up having a little bit more ring strain. Cyclobutane puckers a little bit also, and it increases its ring strain, but it already was highly strained to start with. Okay, so now what we're going to do is we're going to look at angle strain, torsional strain, and steric strain. And when do we have these in the ring? We kind of already have talked about angle strain, but now we're going to talk about torsional and steric strain. Torsional strain, remember, comes from electrons and bonds being in the same plane and that they repel each other. Steric strain comes from atoms basically bumping into each other. We don't have steric strain or much steric strain from plain unsubstituted rings. However, when we have substituted rings, we can have steric strain. In cyclopropane, the molecule is planar, and so the hydrogens must be eclipsed. So a cyclopropane not only has high ring strain, it also has eclipsed bonds that add torsional strain. If we put methyl groups on here, here, and here, they then would have steric strain. Plain cyclopropane has angle strain and steric strain, torsional strain. Substituted cyclopropanes also have steric strain. So you tell me, what are the strains in cyclopropane? Ring or angle strain and torsional strain. And if we have substituents, we then would have steric strain. Cyclobutane. It slightly puckers in order to keep the bonds from being eclipsed. If I flatten out the cyclobutane structure, I would have eclipsed hydrogens. So it puckers slightly to reduce some of that torsional strain. When it does, it increases the angle strain slightly, but less than the reduction in the torsional strain. So this cupped or puckered shape is lower energy. So you tell me, what strains does cyclobutane have? Angle strain and torsional strain. And if we did put substituents on it, we would then have steric strain. There's more if they're adjacent to each other. So 1, 2 would have more if it was cis 1, 2, less if cis 1, 3. If you have trans, there's no steric strain between the substituents. There's a tiny amount of steric strain between the substituent and the hydrogens, but it's minor. Cyclopentane. If I look at cyclopentane, it has a puckered shape. Why? Because if it's totally planar, all the bonds are eclipsed. So what it does is it puckers into what we call the envelope conformation, and that staggers the hydrogens, reducing the strain. The angle strain is minor. It's not huge. You'd have a small amount because it's puckered. If you were to flatten it out, there would be no angle strain, or very little, almost none. But it's puckered, so there is a slight amount of angle strain. So you tell me, what strains does cyclopentane have? The strains that it has, a tiny bit of angle strain, torsional strain that's been greatly reduced by puckering, and steric strain, especially if you have cis substituents. Cyclohexanes are the most common ring that we have, probably because they are the most stable of all of the rings, the least amount of strain. It's the most common ring in nature. However, there's a lot of cyclopentane rings, and there's even a couple cyclobutane and a few cyclopropane. Cyclopropanes are actually reasonably common in nature. Remember, the ring is not planar. We will draw it flat a lot of times, but we always have in our mind that it is puckered in this chair conformation. When it is in this chair conformation with one carbon out of the plane down here and one carbon out of a plane up there, it causes all of the carbon-hydrogen bonds to go into a staggered position, which reduces its strain, and it also causes the bond angle to be reduced from 120 down to 109.5. So a cyclohexane ring that has no substituents actually has no strain in that particular resting position. Of course, it's going to flip back and forth, and when it flips back and forth, it actually causes a slight amount of strain during the flipping process. What's the flipping process? This carbon would actually flop down and this one up. Okay, so now you tell me, what kind of strain does cyclohexane has? The only kind of strain that you're going to see is no angle strain, no torsional strain. When it's in the chair position, the only kind of strain that you're going to have is the strain of substituents, and we're going to go through that in great detail in another lecture.